Now, the first thing I want to do is recall what happened with line integrals. And let's consider an example. And I'm going to badly draw my coordinate system. But consider two different curves, C2 and C1 going from the point A to B. And we're going to consider the integral from A to B of f dot dr along either C1 or C2. We're going to use the example that was given as a group problem where f of xy as a vector is 3x squared plus y squared I hat plus 4xy j hat. This curve was just a straight line. And this curve is part of a circle. And in doing these, we used a parameterization with cosine of 2t and sine of 2t. Now, when I do these two integrals, I get two different answers. And if we recall from our vector calculus, the reason we get two different answers is the integral around C1 of f dot dr does not equal the integral of around C2 of f dot dr. What do we know about the curl of f? Does anyone remember this sort of basic vector relation and identity? It's not zero. Right? The curl of f equals 0 is special. Why? It makes it a conservative function, and then the integral is path independent. We're going to, once we get through all our vector integrals, we're going to come back and prove that whole thing in big detail. But let's just remember, if the curl of f equals 0, then it should be path independent. Well, if I look at this quickly, and I take the curl of that function, can anyone tell me, how quick are you with curls? What's the curl of that function, the magnitude of it? What two derivatives am I going to take? Curl, come on. Of what? Partial with respect to x of what? The j component. So in this case of 4xy.
Minus the y, partial with respect to y on the other.
And so what do I get?
4y minus that's 6y.
Excellent, which does not equal 0. Notice, how could I adjust my function? And there's lots of ways I could do this. But what's a simple adjustment I could make that would make this 0? To say to the x component. How could I adjust the x component of this function so that my curl is 0? Say again? Change the coefficient of 3 to 2. Because then this becomes what? 4y, and 4y minus 4y is? So I encourage you to go back, redo that group problem along those two curves, and you should get the same answer along both paths for this. Now, an important thing I want to point out is in the group problem, I just gave you the parameterizations of the curves and the initial and final point. Some of you, I know I haven't graded it yet, some of you actually integrated over this curve. You will, of course, get full credit for it because I didn't specify whether to go from A to B along this part of the parameterization or along this part of the parameterization. Now, turns out, for this circle, these two pieces are equal and opposite. So if you go either this way or this way, you do actually get the same answer. Not because of not because the curl's 0, not because anything like that, just because of another symmetry in the problem. So you will get the same answer. You get a different answer by a minus sign if you go this way or this way, because the direction matters in a contour integral for the minus sign. Now, the big question therefore is why, when the curl of f equals 0, does the path not matter? And again, we're going to do the full proof later on in a different lecture, but I want to motivate right now a key feature. And the fundamental idea is that this object, when the curl of f is 0, is a total differential. This is a key idea. I mentioned it to you. It's one of those math ideas that comes up a lot. It's particularly important in thermodynamics and stat mech, because when you do a thermodynamic problem and you're changing, say, entropy and energy, you find out the two of them separately are not total differentials, but the internal energy related to ds minus TD, dE minus TdS becomes a total differential. So when you combine the two, you get one. So we want to know when this is a total differential, because if I integrate a true total differential between 2 points, that is the case where I can write it as an answer. Well, actually, no. In this notation, I want to use w's. I can just write it in terms of whatever this function is at the endpoints. That's the kind of the definition of a total differential, is that independent of the path, I can just take the function and compute it at the two endpoints. And notice what we have, right, is in a sense an integral over the path, okay, being converted into an integral over the endpoints. So the endpoints get the function. This is, in a sense, an integral because it's a sum, right? I only have 2 points involved in my integral, the two endpoints, so it doesn't really look like an integral, but it kind of is. This gets the function. This gets the derivative. So using that principle I stated at the beginning, I'm kind of motivating and justifying that this thing doesn't care about the path suddenly, because I'm relating any curve to its endpoints. Just like before, the integral over any volume, it gets related to the surface that's enclosing it, and so on. And yeah, no, go ahead.
So is this like saying then that we can, if the curl's 0, we can define a potential?
That's exactly the same statement. And what I want to highlight here is this, this becomes true for any path. But it's really true only because that thing is a total differential, right? This statement is this general reflection of that general principle I mentioned before. So the integral over any path, because it's enclosed by these two endpoints, is the function evaluated at the two endpoints. And now we can see the connection between this and the potential. Let me just do it in this little corner here, right? If you recall our definition of gradient, right? The gradient of phi dotted into dr, we can write that as the gradient of phi dotted into r hat, a little unit vector along the direction of dr. So r hat's a unit vector along the direction of dr, and then we're just multiplying times the magnitude of dr. This object here, anyone remember what it was defined as, how we got it?
Oh, it's the directional derivative.
It is, well, it's the total derivative of phi with respect to r. Along that direction, basically, yeah. And so now we see, whoops, that by definition the gradient of phi dotted into dr is a total derivative d phi. And so if I have the integral over any curve of the gradient of phi dotted into dr, that's the same as the integral d phi over the curve, which we've just, I haven't proved for you yet, but I've justified is just phi of b minus phi of a, where these are the endpoints. And that's just, I wanted to do it this way. It's not necessarily the standard way you see it in a math class, but to highlight why structurally this is fundamentally no different than any of the other vector integral identities we're going to derive. It's fundamentally the question of, do I have a total derivative here over some region? Well, then I get to use that function over the endpoints, or the boundary of the region. And the ultimate connection, of course, is, so if the function f is the gradient of some function phi, then the gradient of f dot dr is a total derivative. And now the integral of f dot dr over any path or curve is equal to phi of b minus phi of a, and is path independent. And so the piece in all of this that's kind of missing in terms of proofs, which we'll do later, is that if the curl is 0, then I can always write f as the gradient of phi. If f is the gradient of phi, the curl is always 0. If the curl is not 0, then f cannot be written as the gradient of phi. And then it is not a total derivative, and the integral depends on the path. You actually have to do it along that path, because I'm no longer allowed to use this idea, because this thing is not a total derivative. And it's when this is not a total derivative that I'm not in that form that I have of the integral over some region of d phi. And so I can't do this. And that's why things that are not total derivatives do become path independent.